presentation. I'm glad to see everyone is showing up. Very few presentations I've been to now that were in person, so this is, I like that we're looking at smaller Zoom boxes. Now this is a larger room. That's excellent. And so before we have the presentation, I want you to get a little background on Olympic Climate Action. It's a group of volunteers that are very concerned about climate change, both locally, statewide, nationwide, and of course worldwide. We have over 800 people on our distribution list. And if you're not on our distribution list, we have sign-up sheets over here tonight. You can please sign up to get on our distribution list. Our membership is open to everybody that is concerned about climate change, which hopefully everyone here tonight is concerned about climate change. So please put your name on this. Before we start the presentation this evening, I'm giving my introductory remarks. I want to remind you that at the conclusion of Dr. Miller's presentation, we're going to have a short business meeting in the back of the room. You can leave if you don't want to be part of the business meeting, but we're going to be looking at nominations and voting on new members to our board of directors for the Olympic Climate Action, and some very minor changes to our bylaws. But so please stick around if you would like to. And I have to look at my notes because I don't remember everything I'm supposed to say here. Again, Olympic Climate Action is, I say we do it both locally and nationally and statewide. If you haven't already, you can always Google our website, Olympic Climate Action, and we have a very active, hot off the wire sheet that describes various actions that are going on around the whole region. Without further ado, I'm going to introduce Janice Berger, who's also on our board of directors, and she will be introducing the speaker. Janice.
Cool. Thanks, Ed. And quick announcement, we only have one flyer because we're not distributing it yet, but we have another program in the future. So mark December 1st on your calendar for Alaska Suite, which is, here I'm going to read because I can't describe it.
And anything you want to post one of those.
Yeah, you can post it. It's an amazing kind of multimedia jazz musicians from Seattle who volunteer their time with images of Alaska and about climate change and a sort of discussion story and music. So that's in early December, going to be in Port Townsend, Sequim, and here in Port Angeles. So please come. But tonight, Dr. Ian Miller, I've known Ian from when he used to work out at Nature Grid, but he's been on the peninsula for, what did we decide, 26 years. And I was thinking, what are some cool anecdotes about why you're interested in the sea? And he said he's the son of a Navy man. So there we go. But he's been studying sea level rise with Washington Sea Grant for a long time, and it's been really, really nice having his expertise here and his willingness to share that expertise with all of us. So thank you so much for being here tonight.
So first of all, I'm going to turn this mic on, which hopefully works. I should say, let's figure out.
There's a button, a big button.
Okay. Does that do anything? Can everyone hear me? In the back? All right. So thank you so much. Again, Ian Miller with Washington Sea Grant. You're here hopefully to hear about sea level rise. That's my intent. The reason that I'm here is because I have, in this role that I have with Sea Grant, which I'll describe in just a second, I've focused over the last 5 or 10 years on sea level rise, mostly oriented towards management in Washington State. So that's kind of my interest, is in understanding the implications of sea level rise here in Washington State in our coastal communities. So the plan for tonight is I want everyone to walk away with a sense of what do we mean when we use this word sea level rise. I'm guessing many of you have that in mind, but just in case. And then, is it already happening in Washington State? Why is it happening, and what does the future hold? So that's the plan. Before we start, so many of you may not have heard of Sea Grant. We are a University of Washington-based program. We're an extension program, so our sort of heritage is in the land grant program, but we're configured differently. We focus on marine and coastal issues, and we don't have county offices like WSU does, but we do have field staff like myself. I live and work here in Port Angeles, operating out of Peninsula College. And mostly what we try to do is create connections between coastal communities in our case, and science or other resources that can help manage the various coastal issues. I work in coastal hazards, but many of my colleagues work in areas like fisheries, aquaculture, water quality, boat safety, all sorts of different things related to the challenges of living in coastal communities. One of those challenges is coastal flooding, and so this is kind of where we launch into the sea level rise theme. Some of you may know what you're looking at here. This is December 27th, 2022, a couple months ago, when a extreme coastal water level event impacted especially much of Puget Sound, less so out here. It wasn't as notable out here, but in Puget Sound, definitely a notable flooding event. A few things made it notable. One, it was widespread. So here's a couple more flooding photographs, one from down in South Sound, one from up in North Sound. So this is a widespread event. It was also unprecedented, and it set water level records at 5 tide gauges in Puget Sound. Those are the ones shown with the red arrows, including in Seattle. And that's notable because Seattle has, by far, the longest water level record, coastal water level record that we have in Washington that dates back about 120 years. So this event set a record. And like most of our flooding events, sort of on the face of it, this event was driven by 2 things. It was driven by the alignment of a high tide with a storm. So to try to illustrate that, I always revert to data. It's both a blessing and a curse. I know that you probably can't see that there, but what you're looking at are predicted water levels for 6 tide gauges in Washington State. These are Port Angeles, Cherry Point, Friday Harbor, Port Townsend, Bremerton, and Tacoma. Doesn't matter that you can see them. The key thing is to note there we have that low tide and then that high tide following it. And then those tide gauges also typically measure weather data. So what I'm showing you now is pressure recorded at those tide gauges. This is air pressure, and you can see the passage of that storm in the pressure information there. And the final thing that I'm going to show you here is what we call the non-tidal residual. This is the storm surge associated with that pressure. When we sort of lower atmospheric pressure, typically during large storms, the sea surface kind of rebounds a bit, if you will, so we tend to get higher than predicted water level during those events. So this was a classic sort of coastal flooding event for our area in the sense that we had almost perfect alignment between the low pressure, that peak in storm surge, and the high tide. They all co-occurred. We get super elevation of the water. We get flooding as a consequence. So one way to think about this, the way that I tend to think about it, is that we go into every winter sort of rolling the dice. Every storm is a roll of the dice. It's a roll of the tide dice and a roll of the storm surge dice. When those align is when we get our extreme events. So in that way, it was kind of a standard kind of storm event, but the theme of the talk is sea level rise, and indeed, as I'll show you, sea level rise is weighting the dice in favor of making these kinds of events more frequent and more extreme. So before we go on, what is sea level rise? So I know many of you probably can't see this, but you may have seen it online before. This is a plot drawn from the NOAA Tides and Currents website. This is NOAA's site where they collect and serve data collected at the tide gauges. We have 8 of them in Washington State. And this is monthly average water level from Neah Bay, dating back to when that station was founded in 1936, I think, if I recall correctly. So a tide gauge has been sitting there collecting water level every 6 minutes since 1936, and then those get averaged into a monthly value. And that's what you're seeing here. And I'm sorry, that's not Neah Bay, that's Seattle. Many of you are like, what are you talking about? So this is Seattle. And you don't have to look at the numbers or anything like that. The key thing to note there is the upward trend in this data set. This is what we refer to as sea level rise. It's the long-term change in sort of an annual or decadal average in that water level. So the reason that I think it's important to think about kind of this definition in light of where we live is that you have to think about all the processes occurring on top of this increasing average. Our tidal cycle, our storm surge patterns, to really start to understand why, say, 6 inches or a foot of sea level rise has consequences in an environment like ours where the water level varies by 12, 13, or 14 feet a day. It's kind of a hard thing to wrap your brain around. It's at least a hard thing for me to wrap my brain around, but indeed it is the case. The other question we can ask as an extension here is sea level rise happening in Washington State? And this is kind of a complicated question, as it turns out. It should be obvious from that Seattle example that I showed you that it is, but we don't have to go very far, only out to Neah Bay, so this is where Neah Bay finally comes in, to see that the tide gauge there records the opposite pattern. Sea level is falling in Neah Bay as measured by the tide gauge. And so with this in mind, it's kind of hard to understand exactly what the ocean is doing. So one of the things that I have focused on, interestingly enough, over the last couple of years is really trying to understand what the land is doing. So we dove into this in detail a couple of years ago because it's important to understand how the land is moving in order to understand what the tide gauges are telling us about the ocean, as well as to understand what the implications are of sea level rise for communities around the state that have very different patterns of what we call vertical land movement. So what you see up on the screen, hopefully, is a map of Western Washington with a bunch of colored symbols on it that represent places that we can actually measure vertical land movement. This is how fast the land is rising up or down. And in this case, the hot colors are places that we think are moving up. Cool colors are places that we think are moving down. These estimates come from tide gauges. They come from GPS stations that are fixed on the landscape. They come from highway side survey markers in some cases. They can all be put together to develop a sense for what the pattern is on the landscape. And one thing that hopefully pops out at you here is that there's a lot of variability, right? We live in a sort of tortured landscape. The signatures of our subduction zone are all over these data. The other thing to note here is these rates are kind of small. They're measured in millimeters per year, roughly how fast your fingernails grow in some cases. However, over years and decades again, they accumulate and they matter in terms of understanding sea level change. And the key thing is, going back to sort of our original question, is if we remove the vertical land movement estimate that we have now for every tide gauge in Washington, this is what we see. So what you're looking at now is time on the lower axis. So this goes roughly a little before 1940 out to 2020. And this is change in feet relative to 1990 to 2010, just an arbitrary zero. And these are in fractions of feet. The thin line is the annual average. And again, this removes the influence of land movement. This is just what the ocean is doing. And then the dark black line is a rolling 20-year average. Again, just looking for that long-term average. And hopefully what pops out at you there is that we do have an upward trend in sea level in Washington State. It amounts to about 4 inches over this record, so not very much. However, I will show you that it does have impacts. And also that we expect that trend to continue. So what are the impacts of that sea level rise? Well, the most obvious and visible one is that we expect coastal flooding to increase in frequency and magnitude, right? This is the obvious signature of sea level rise on the landscape. Showed you this photograph before from that event in Port Townsend in December of last year. What's interesting about this particular event, at least to me, is that this is the first event that I think we've been able to actually calculate how that small amount of observed sea level rise that we have in Washington, 4 inches over the last 60, 70 years, not much at all, has changed the likelihood of this event occurring. So again, this kind of record-breaking event. If we had not experienced sea level rise in our area, this event would have had a very fractional, I don't know if you can see that number, 0.125% annual chance of occurrence. That equates to something you'd expect on average once every 800 years. Whereas with sea level rise, this now has an annual chance of occurring of about 1%, something we'd expect on average every 100 years. Right? So this is kind of the impact of sea level rise in terms of changing the frequency of events like this. Sea level rise also has other less visible and obvious impacts. This particular photograph is from the Chesapeake Bay during a fishing trip I was on with my dad. And what I was trying to take a photograph of, if you can see there, is this ghost, what they call ghost forest there. Here, we refer to ghost forest as being associated with tsunamis. In the Chesapeake Bay, it's associated with forests attempting to retreat up elevation in association what is there, a much more rapid rate of sea level rise than we are currently experiencing. But these kinds of habitat responses to sea level rise are expected, they're observed in other places around the world, and we do expect that we will see them emerge here as well. So what's the driver? This is a climate-related sort of process, and really associated, and by the way, I am not going to dive into the conceptual model of climate change. I'm making an assumption that everyone has a sense for sort of the driver of climate change, and in particular, that the response is that an accumulation of a heat energy in the Earth's system. There's two processes that drive sea level rise that respond to that. They're both processes that everyone has probably interacted with today. And that's why I visualized them this way on the screen. One is that if we expose ice to this heat energy, it tends to have a harder time staying in state as ice, and tends to, over time, transfer into its liquid form water and then flow into the ocean. The second is that as you warm water, it expands. Can we get some lights? Because I brought demos, right? Got to do some demos, got to have some colored water. So these are both, again, easy things to model and visualize. These are examples from your own home, obviously, but just in case, I brought some sort of examples to try to model both of these things. This is kind of a thermal expansion demonstration, and I've added some heat energy to it. I don't do this one very much, so I have no idea how long it'll take. But I've got this little green thing that marks our sea level, and we'll just see how that responds to this additional heat building up in this fluid. Now this is just like a mercury thermometer for those of you that remember those, but you may not be aware that water has this same property, and it occurs in the oceans. The other big process is melting of land-based ice. So we're talking here not about sea ice, ice that freezes from the ocean, since that already displaces water. So when it melts, it doesn't contribute to sea level rise. We're talking about masses of ice that are perched on land, so that when they melt or lose mass through time, that's just an addition of new volume into the ocean basin. So kind of the easy way to demo that, or to model that, hopefully without a big mess, is that in this case, I'm going to make a land ice system. So I've got my ice perched up on land right here. And in this one, I'm going to add my ice into the ocean. And then in both cases, I'm just going to mark sea level. Is that right?
Pretty close.
Okay, and we'll just see how those respond over the course of the next 10 or 15 minutes. Okay, thank you. Okay, so in an effort to try to sort of explore both of these processes, I'm going to use this visualization. This is what's called a sea level budget. This work was done by the European Space Agency, but it's been done by a lot of groups. I just chose theirs because they had a nice white plot that I could draw on. And so what you're looking at here, we've got time. I know you can't see that in the back. This is 1994 to 2017. So this is kind of recent observational period. And then this is kind of a change, a relative change in sea level. This is in millimeters, but I'm going to transfer everything to inches. So the curve that you see on there is observed global average sea level. This is actually measured from space using what's called radar altimetry. So this is a satellite system that can measure very accurately changes in the Earth's surface using radar. And they are sort of continually making measurements of the ocean and developing these estimates for the mean height of the ocean surface and then how it changes through time. So this is a measurement, direct measurement of sea level rise. So that's what you're seeing there. It equates to about 3 inches since 1994. So a little bit of a faster rate globally than we observe locally. That's an interesting thing that we'll set aside. And if anyone wants to nerd out on that afterwards, I'd be happy to do so. So the first thing we're going to look at is this idea of thermal expansion. We warm water up and it expands. The consequence in the ocean basin, which we can view as being fixed, is the height increases as we warm it up. The warming here is minuscule. We're talking about fractions of a degree potentially, but because of the volume of the ocean, it can manifest as a measurable change at the surface. So how is this actually measured? Since the early 2000s, it's been measured with what are called Argos floats. So that the yellow device up in the corner is one of these floats. These are autonomous thermometers, basically, that are floating around the ocean. All these green dots represent one of these things. There are hundreds, if not thousands of them deployed. They are designed to sort of autonomously sink into the ocean, measuring temperature as they go, and then come back to the surface, transmit their data and their location, and then do it again. And they do it until they get destroyed or they wash up on the beach or whatever. And so from this data set, we can add the component of this budget that is associated with that thermal expansion. And so that's what's illustrated here. These measurements have been made since early 2000. This bit before here is kind of like a modeled estimate derived from that. And in total, that contributes about 1 inch since 1994. So about 1/3 of the observed. And then land-based ice we can also observe. So what you're seeing here is an animation published by NASA. This is another space-derived measurement, in this case of gravity. So this is derived from the GRACE satellite mission launched in the early 2000s. This is a set of satellites that are circling the Earth, and based on how far apart from each other they are, very clever people can estimate how the mass of the Earth's surface is changing. And so over time, you can develop this record, this actual measurement of changes in mass of places like Greenland. And so that's what you're seeing expressed here. There's also estimates that can be derived for Antarctica, which is another big contributor, as well as mountain glaciers. And you saw the animation play out there, but Greenland probably doesn't come as a surprise to any of you, is losing mass currently, as is Antarctica and as are mountain glaciers. So all of those contributions together can get added to the budget here. So that's what I've done here. 2 inches since 1994, associated with that addition of new volume to the Earth's surface. With also a very interesting, some of you may have noted, oh no, there's a laser, I'll just point awkwardly. Some of you may have noted this acceleration, sort of in this recent time period, that you can see is associated with these land-based ice dynamics making increasing contributions to the ocean basins. And the other thing is that red line up at the top is the sum of these two, right? And so we can use that as a way to say the budget is mostly closed. There's little gaps and wiggles in there, but for the most part, these two components explain the observed pattern over this historic period. These are the two main drivers, and both of these are climate sensitive. So that begs the question, how much more sea level rise can we expect? And there's really kind of two fundamental answers to this question. One is that it depends partly on how warm we make it. Some of you are likely familiar with something that looks like this. These are temperature projections that are associated with a set of what are called emissions scenarios. These are storylines that are crafted to sort of describe plausible future scenarios of emissions of long-lived greenhouse gases that are then shared around the world, and basically anyone who's modeling climate change will typically use those, and that way they can compare their work to sort of the next person over or the person in the next country and sort of get a sense for what that looks like and how their models compare. And of course, if we, as a global species basically, are able to figure out emissions that track in this kind of, that sort of align with these lower scenarios, the expectation is we have a lower global average temperature associated with that, and because those two sea level processes are directly associated with those temperatures, we expect less sea level rise. By contrast, if I go the other way, if we follow the upper emission scenario, the reverse is true. We expect more sea level rise more rapidly to occur in response to this. But there's also a large degree of uncertainty associated with uncertain processes. I know no one can read this probably in detail, but I decided to throw this up here to illustrate this because this was today's hot media topic. I think 3 people in the lead up to the talk brought this up with me. And this is a paper that was published, interestingly enough, last year. This is a paper, one of many that are coming out, associated in particular with trying to understand uncertainty in Antarctica in particular. So Antarctica, for a whole variety of reasons, is a big potential contributor to sea level rise. It is by far the largest mass of land-based ice on the globe. And it is also by far the hardest one to understand. It is very big, it's very complicated, and it's a hard place to work. And so as a result, it's just a hard place to understand. As a result, a lot of papers use modeling to sort of try to get around this problem, use computer models to try to understand what is happening in Antarctica. This is a modeling paper. This one is about what are the possible historic trends in ocean temperature around Antarctica. And the question they're trying to get at here ultimately is, can we explain why we have observed mass loss in Antarctica over the last 20 years. So those gray satellites that I showed you the animation from Greenland also show mass loss in Antarctica. The weird thing about that is that, unlike Greenland, Antarctica still is below freezing most of the time. And so there's other explanations beyond just sort of warming that need to be invoked to try to explain what's happening in Antarctica. So I bring this up to note that this highlights that work is happening to try to explain what we observe now in Antarctica. And so once you start thinking about what to expect in the future, it becomes, the uncertainties only grow from there. It's a difficult place to work. The other reason that I chose this paper to highlight is, I like the sweaters, no, I'm joking, is that the media reporting associated with it drew my attention immediately. This was the headline associated with that paper: humans have lost control of the West Antarctic ice sheet, and it could cause global sea levels to rise by 3.2 feet by 2100. The few things that caught my eye here, just to note, is the paper was not about sea level rise. And so that was kind of one thing. But digging into this media reporting, the other thing that I noted in this paper was they found a few people to provide quotes along the lines of, when you see a projection from, say, the IPCC, which is the international sort of body that does sort of global projections, you should just double those numbers because they're just getting it wrong. And I think the sort of partly to be provocative, but partly because this is swirling in my head, I want to spend the last few minutes making a few points to sort of suggest maybe that's not the case, and also that doesn't change anything about what, the planning that we should be doing, I think, as communities, coastal communities associated with sea level rise. So, a couple of points. Number one, what you're looking at here is projections for Washington State. These were projections that I was part of putting together, published in 2018. They are what we call probabilistic. And so you got time down here, change in sea level and feet over here, the usual sort of routine. And then you got a bunch of lines over here that are associated with different percentages. The idea behind this is to show the range of uncertainty in possible future sea level for Washington State. And the idea is that up in the top part of the curve, you've got these numbers like 4, 5, 6, 7 feet that are shown as being low likelihood, but can't be excluded as possibilities, right? And that's important to consider. They can't be excluded. However, we also have this likely range, which is shown in the gray bar. It's kind of in this 2 to 3 foot range by the end of the century. And the thing that struck me about that was that kind of 2 to 3 feet by the end of the century, even though there's a lot of sort of talk about how much models have changed, and especially when it comes to sea level rise, there's so much uncertainty, that has been a very consistent assessment number for a long time, multiple decades. So I've got 2 examples there from the IPCC from 2014 and 19, in which their median estimates fall right in that range, 2 to 3 feet by 2100. The second thing to note is that we can also increasingly use what we observe as a way to assess where we are tracking relative to projections. So that's what I've done here. I've taken those observations I showed you earlier in black, and the red are the probabilistic projections I just showed you. These are for RCP 8.5, and the thing to pay attention to is the dark black line sort of tracking in that what we call the likely range, sort of in there, right? So again, the observations currently track in that intermediate range. The third point is that kind of when these papers come out about models, or we make observations, or we sort of see media reports about things happening in certain parts of the world, we have this expectation that they don't align with models, but it's worth pointing out that if we go back to our observed sea level and we extrapolate the last 10 years out to 2100, we get to about 12 inches of sea level rise by 2100. That's just extrapolating our observations. Whereas the projections of the components, so we've got our thermal expansion component and our ice vault here, and our land ice addition of water melting component. You can see the projections over there these are the median projections from the most recent IPCC report. AR6 came out last year, 2022. 11 inches from this component, 14 inches from this component. And the point here is that both of these we expect to accelerate in the coming years and decades by 2 to 3 times to be able to reach just that 2 to 3 foot intermediate territory. So in other words, there will be very obvious signals from the landscape. Things that we have not yet observed will happen in Greenland and Antarctica in particular, I think, that we'll read about. And there'll be this impulse to sort of say, we did not expect this. But in fact, this is exactly what these models are suggesting should be happening. It's kind of sad to have a hypothesis supported like this, but this is what we expect to see occurring, to reach even that 2 to 3 foot range by 2100. And then the final point I'll make is that it's obviously good to get your planning scenario right? If we do expect, say, 6 feet of sea level rise by 2100, it's important to get that right. But it's worth noting that we have plenty to think about as communities with just 2 to 3 feet. So in terms of embarking on planning, trying to figure out where our vulnerabilities are, this is a great place to start. And to highlight that, I'm going to use a just published assessment. This is from Jefferson County. This was released a few months ago, in which they mapped various assets in Jefferson County, buildings, septic systems, wells, and compared them to sea level rise scenarios. And they found for their plus 2 foot sea level rise scenario, so adding 2 feet, that the number of home or buildings in that at-risk zone increases by almost 3, and the number of wells almost doubles in association with that. So this is plenty to do to sort of try to think about these vulnerabilities, even absent of those more extreme scenarios. And so, just by way of ending, thank you. I'm excited to hear if there's any questions or discussion. I have my contact information down at the bottom, so if we don't get to anything, that's how you get in touch with me. And I also just wanted to end, one of the things, I do a lot of this kind of stuff, and there's always a bit of like a downer thing to it, right? I have like a little bit of a Dr. Doom reputation, and so I like to end on a high note. So this is my effort to end on a high note. I just want to point out, I do a lot of work with other colleagues around the country from other states who are engaged in the same kind of thing, trying to figure out how do we go about sort of planning for this particular stressor for coastal communities. One thing I hear frequently is that Washington State is viewed as a leader in this realm. And I think that there's some evidence to support this. I just threw these up. This is, again, that Jefferson County assessment. This just came out. Port Angeles Climate Resiliency Plan just came out. Communities are starting in on this. And I know that there's many who feel they should be doing less. There's many who feel they should be doing more. But in my mind, I always view it as a positive if it's just being tackled as an issue. So to me, that's the positive, and excited to hear everyone's responses. Thank you. Thank you. Yes. Do I just go for it? Questions?
Yeah.
Okay.
We've got like 20 minutes for questions.
Early on in the presentation, you had a graph of the sort of net aggregate sea level rise in Seattle versus the net aggregate sea level rise in Neah Bay.
Yeah.
If you had one of those for Port Angeles,
Yes.
would it be pretty level?
So the Port Angeles tide, we do have a tide gauge in Port Angeles, so we have that record. The bummer is that it was installed in the 70s, and so we don't have anywhere near the length of record that, I forgot to totally mention, Seattle dates to 1898, Neah Bay to 1936, I think, Friday Harbor is 1936. Most of the other tide gauges are newer than that. And so the record's not long enough to really establish a trend without some statistical trickery. So if you go onto the NOAA website and look at the trend they have, it's essentially no different from zero, dating back to the 70s. And I think that, like Port Angeles is interesting because if I go back, sorry about this, give you a seizure. If I go back here, this is one of the things I think that's so cool about the strait, is that it's like a seesaw, right? And so uplift happening out here in Neah Bay, subsidence happening in Port Townsend, and somewhere in the middle is an inflection point, a 0 point. And I don't know where that point is.
I look at your maps on the wall at Faro every Saturday
Yeah.
and tell people where not to buy property.
Yep.
And it strikes me that Dungeness is just a whole lot worse than Port Angeles. You can hardly find any place that's likely to be underwater by 2050 in Port Angeles.
And that's not because of vertical land movement. That's because it's much steeper, right? One of the things that characterizes our landscape, for the most part, is that it's relatively steep. And so there's not a lot of places that are extraordinarily vulnerable, especially when you look at them in map view like that, right? Where you're sort of looking, your eyes drawn to those big blue blobs that tend to occur in places that are low-lying and flat. So the Dungeness River Delta is is our good local example of a place that's low-lying and flat, likely a lot of exposure there. Whereas Port Angeles is higher and steeper. And so you just don't have that kind of exposure. Now,
I'm going to change my spiel.
One thing, so I recently, we're in the middle of a project in which we're trying to map sea level rise vulnerability onto parcels in Puget Sound. And we haven't extended it out to the strait yet because we don't have good elevation data. We do now, but we have to sort of do the analysis. And one of the things we found from that, so we gave every parcel a score. And we found 3,000 parcels out of a total of 111,000 that fell into that highest vulnerability category. And so very relatively few, something like 2.8% of the total that fell into this high vulnerability category. And one of the reasons is that we live in a steep landscape. And so we have a fundamentally different, I think, opportunity than many regions of the country, right? Notably Florida and parts of the Central East Coast that are, much flatter, much more low-lying. Like, my takeaway from that process was that if we sort of can focus attention somehow on a fairly small amount of parcels, we gain a lot of vulnerability benefit. Now, let me point out, though, that when you look at things in map view, it doesn't always reflect your real vulnerabilities. So what the city of Seattle, for example, has found is that they really had to think about things like stormwater outfalls and other drainage systems relative, even though it's sort of a similarly steep landscape and there's not a lot of low-lying vulnerability there, they had these other vulnerabilities they identified that they are adjusting. So that's worth pointing out. That was a long-winded answer, I'm sorry.
I like long-winded.
Yeah.
You mentioned, I think when we were talking about this, about ideas, well, first off, maybe identifying the worst case for the most vulnerable places, and then ideas of what are some solutions. I know that things like for coastal management, shoreline management, things like hardening and seawalls and stuff are not a good answer for a lot of things because they're so bad for habitat, fish, etc. So what are some adaptation, I guess, most vulnerable places in our county, and then what are some adaptations that might be worthwhile?
Yeah, so, fundamentally, when we talk about options for sea level rise, it's the same set of options that we talk about for any coastal hazard. It's protect, right, which is typically in association with, engineered structures of one kind or another that have their pros and cons. It's adapt, doing things like, the most typical example is for buildings that can be raised, that can be flood proofed, that can be engineered so that if they do get flooded, the impacts are not severe. And this occurs in our county all the time, mostly through our building codes. If you drive to, say, Three Crabs, many buildings are elevated in association with following building codes, and that provides a degree of adaptability for flooding. And then the third is retreat, right? You move stuff out of the risk zone, and all of them have costs and benefits. None of them are easy, but one of the things that we try to do is kind of present information that can be used to weigh those costs and benefits, but oftentimes it's a very site-specific assessment that has to be done, at least currently, in Washington State. In Clallam County, in terms of where is most vulnerable, I'd love to be able to answer that rigorously, because I really love the idea of trying to identify vulnerabilities that maybe we don't think of, because what we've done for the Olympic Peninsula is just largely mapping. So when you do that mapping and you end up with these kind of big blobs, those are in the places that are low-lying. And so Dungeness always pops out as an obvious place that's vulnerable. It's low-lying. It's currently in the flood zone. There's every expectation that flooding there will increase in frequency and magnitude. However, it's worth noting that we also, in that assessment that we're working on, in which we're trying to map vulnerability, we include parcels on the tops of bluffs, because one of the mechanisms, one of the hypothesized responses of shorelines to sea level rise is increased erosion. And so on a bluff top, that can be especially impactful. And so one of the things that if we can really rigorously look at these things, that I think we find is that we have much broader vulnerability than we think if we just look at a map where the Dungeness River Delta pops, for example. Yeah.
What do you think the spits are going to do? Will they grow naturally?
Yeah, so that's a great question. I think it depends on the rate of sea level rise. And in fact, I think I pulled this thing out that I was going to talk about, and then I abandoned it at the last minute, but I thought it was kind of cool. It's horrible to look at, but so what you're looking at here is a really cool study. This is a paper that was published in 2004 by two Canadians. And what they did is they went all over the eastern Strait of Juan de Fuca, and they mapped the seafloor, so bathymetry, of the seafloor. They used what's called CHIRP to look into the seafloor, to look for layers. And then they also collected samples in which they hoped to find organic material that they could date. And they used this to make what's called the sea level curve for the Strait of Juan de Fuca. This is associated with deglaciation. So they were sort of interested in what was sea level like, from say 14,000 years ago to the present, make that curve. And what they found was that sea level rise here, associated with deglaciation, was fastest between 10,000 and 6,000 years ago. So that's when, globally glaciers were just dumping massive amounts of meltwater into the ocean. Sea level was rising very rapidly. The rate that they determined was an average of about 12.5 millimeters per year. So why that's germane to that? So our current rate's probably in the sort of 1 to 2 range millimeters per year. The reason that that's important is because the other thing they have in here is they mapped relic spits that were off of the Elwha. So those of you that fish, you kind of know these spits well. They're referred to as the humps, and they're a great place to catch fish. But they are relic spits that were drowned by sea level rise. And so kind of what that tells us is that there's certainly some rate at which those spits will just be flooded and drowned, right? But presumably at lower rates, they might be battered a little more, just as sea level rise creeps up, and may migrate, may be broken. We don't totally know what to expect entirely. But if there's a real acceleration, I would expect they would just be drowned.
Is Annisquam healing now that the Elwha, now that the Elwha dams are out?
Oh man, loaded question. Is Enisook healing?
I don't know the proper.
Well, Enisook is getting sediment supply from the Elwha dams. It's not getting a whole lot, and Enisook has so many other alterations that have happened to it. It's hard to say exactly what healing means, I guess, in that context. But it is getting sediment from the dam removal. Yeah.
Yeah, I noticed that in last year's IPCC report, it actually said we're currently not on the 8.5, RCP 8.5 track, but a little bit below that.
Yeah. Yeah, which is interesting. I don't sort of spend a ton of time looking at those emission scenarios, but I do think that tracking them as we move forward in time is useful. My understanding is that we're still in this period of time when we can't really say, because they're so kind of like close together, if you will, that we haven't hit a point where we can sort of reliably sort of identify a divergence, but I could be wrong about that. So it'd be interesting to explore that a little more.
I think it was more on the energy, actual emissions more than modeling.
Yeah. But I do think that's, as we move forward, that's a very useful thing to understand, especially because, we tend to sort of, in planning processes, my experience has been the default is to select the high emission scenario because there's so much uncertainty about what to expect, and it gives you sort of a degree of, buffer, I guess. And, the question would be whether we don't do that anymore. So, yeah.
Is there an explanation why sea level rise is not uniform across the globe?
Oh, thank you for asking that, although it's a horrible answer. But I did bring it up because we do have a lower rate here than the global average. And I kind of alluded to that. And just to illustrate sort of the question, I'm going to, here's the map right here. Okay, so what you're looking at here is a global map of, this is that based on altimetry, right? So this is satellites actually measuring sea surface height over the since the early 90s. And I know at the bottom you can't see it, but there's a scale that goes from, I think it's -15 up to 15, and this is in millimeters per year. So the current global average sea level is 4 millimeters per year. So we're kind of in this yellow territory. So basically anything that is hotter colors than yellow are places where sea level is rising faster over that time period. and places where it's cooler colors or kind of whitish is places where sea level is rising more slowly. There's a whole bunch of reasons that this is happening, most of which are associated with, one, we live on a spinning planet, right? We're not filling a bucket, we're filling a bucket that's being spun at the same time. And the other is, I think, really fascinating to consider, and which is that you have these large masses of ice. So I'm pointing to Antarctica here, which in this map view is like stretched all the way across the screen, which, you know, are massive volumes and massive masses of ice. And as that material is lost into the ocean, the gravitational dynamics between that ice and the ocean changes. So there's a gravitational influence of that ice on the surrounding ocean. So one of the things that you frequently see, you can't really see it for Antarctica because the data aren't good from the altimetry, but if you look up at Greenland, where again, Greenland's losing mass, you frequently see blues and whites because even though there's a massive amount of volume of water being added to the ocean there, because of this gravitational response, sea level typically falls. And again, this is not what the land is doing. This is what the ocean is doing, right? So this is an ocean response. So that's another reason why there's regional variation. Where we live in Washington, it's not yet totally clear why we have a slightly lower rate than the global average. My hypothesis is that we are actually experiencing some of that gravitational benefit from melting glaciers in Alaska. So, hypothesis, I haven't found anyone to pay me to figure that out yet. I'm working on it. Yep.
So you are postulating that the mass effects on the plates, as opposed to centrifugal effect of the circulation, of the rotation of the Earth, those two are working in opposite, or?
Not necessarily in opposite, and it's not mass effects of the plates, but of masses of ice, right? So this, what they call sea level fingerprinting, is associated with redistribution of mass from these big chunks of ice. Antarctica, Greenland, glaciers around the globe. So, you know, when they lose mass, that's mass transferring from those bodies into the ocean. And so that changes the gravitational dynamics between those bodies of ice and the ocean itself. So one of the consequences for us is that it's, you know, just to make this more horrible, I think I have somewhere. This is a truly horrific slide deck.
Just to complicate it further, does isostatic rebound from places being released from ice, is that like long gone, that effect?
No, it does, and it matters. It tends to be fairly small. And so we see it here as an influence on land movement, but it looks like the tectonics play the larger role, especially out here. Once you get into North Sound, that may change, but it's kind of hard to tell them apart sometimes. So this is a sea level fingerprint model for Antarctica. And what this is intended to try to convey is that if you lose, I think this is expressed in feet, so if you lose the equivalent amount of mass from Antarctica to raise global average sea level by 1 foot, this is actually how it would distribute around the globe. So the blue is actually sea level fall, right? As a consequence of that loss from Antarctica, sea level near Antarctica would fall, and then places that are distant from Antarctica, northern hemisphere, would see more than a foot as a consequence of that. So this is again why I think...
Is there any way to make that intuitive?
I know. I just think about it for like 5 years. I don't know, like it's taken me a long time to wrap my brain around this. And I'm not totally sure I got it.
It helped maybe visualize it a little bit. You think about the tides, and the moon travels around the Earth, which is orbiting the Earth, And if you visualize the Earth as the obloid spheroid that it is, as the moon travels around, the water bulges out on either side and travels with it. And so the gravity of the moon is pulling the water off to one side, and in some places it raises as much as 30 feet based on other effects. Around here, 7 or 8 feet. But what he's saying is the Antarctic ice sheet is such a mass of water sitting on top of the land that it's actually drawing the ocean up against it a bit more than if the ice wasn't there. So as the ice melts, that attraction to the Antarctic ice sheet becomes less and less and less, and the water just flows away from it. So this would be a reversal of that attraction that you would see similar to the tides of the moon. Only that ice isn't orbiting the Earth, so that tide doesn't move around. It just stays in one spot.
And it's a lot closer to the water than the moon is.
Yes.
So
And the attraction is, related to the distance. So, does
So
that
cool process. I think of it more simply as the ice hugging the ocean.
We have time for maybe just one or two more questions.
Yes.
So what are your thoughts on the Thwaites Glacier?
So Thwaites is an interesting one because it is currently the focus of a lot of interest. It's got a few things working against it. Probably the biggest one is that it has what's called a retrograde bed. So the glacier sits on a bed that's sloped into the continent. And so the concern is that it can have sort of like a threshold-based kind of runaway effect, where if the ice sheet at the end of the glacier, so in Antarctica, most, if not all, of the glaciers have an ice sheet in front of them. And that ice sheet serves to kind of buttress and pin and protect that glacier from other melt processes. Right now the worry is that if those ice sheets start to fail and go away, and that glacier starts to retreat on that downward sloping bed, that it could go quite rapidly. And the downside from our standpoint would be that it's a large glacier. I can't remember exactly the equivalent sea level it's